And by and large, that is true on the maps. But in reality, the age of the old red sandstone sedimentary facies in Scotland certainly extends into the Carboniferous, and it also probably extends into the Silurian as well. So there's the upper Old Red Sandstone. The lower Old Red Sandstone, these pale brown outcrops to the south of the Highland Boundary Fault, and in a series of little bodies near the Southern Upland Fault, are the lower part of the Old Red Sandstone. The Old Red Sandstone is defined by it being a continental sandstone conglomerate facies. There's up to 9 kilometers of red sandstones and conglomerates, alluvial fans, fluvial, lacustrine in origin, and the upper parts of the lower Old Red Sandstone contain fish and spores that are identical to species that you find in England and Wales. The lower parts of the lower Old Red Sandstone contain earliest Devonian spores, and they're associated with volcanic rocks that may be older in part and are part of the lower Old Red Sandstone sequence elsewhere, and these volcanic rocks yield ages between about 410 and 415 million years, which is close to the Silurian-Devonian boundary. There are also lower Paleozoic rocks in the Midland Valley. Not many, but some. There are a number of small areas that lie close to the Highland Boundary Fault, and also others that lie close to the Southern Upland Fault. So you've looked at the map for Stonehaven. Stonehaven's right in the northeastern edge of the Midland Valley up there. So there's a very small area of Silurian rocks and also Ordovician rocks in the northeastern part of the Midland Valley there. That's where the Perth and Stirling maps are, in the central part of the Midland Valley, near the Highland Boundary Fault again. And again you saw, you didn't actually see any older rocks there. Down near Glasgow there are again some somewhat older rocks. Around the Southern Upland Fault there are Silurian rocks in this region here, which is where the Hamilton map is, south central Midland Valley. And in the southwest of the Midland Valley, in the neighbourhood of a town called Girvan. And there's also some just near Edinburgh as well. These lower Paleozoic rocks within the Midland Valley provide the only link that we have between the geology of the Highlands and the geology of the Southern Uplands. So they're very important in terms of understanding the evolution of Scotland as a whole during the Caledonian orogenic events. And as you know, you've looked at their relationships in the practical. So we're going to start by looking at these these lower Paleozoic rocks along the northern margin. So here's a schematic of the northern margin with the Highland Boundary Fault. And notice what happens down here. It gets dashed as it approaches Arran. This is the biggest contrast zone in the geology of the UK, from the metamorphic mountains to the north to the sandstones in the northern Midland Valley. In the north, as you will remember from last week and from your test, we have the Dalradian, and this was metamorphosed and folded into major nap structures such as the Tay nap around 470 million years ago. And that's the boundary between the Arenig and the Llanfian in the lower to middle Ordovician. We also know that within the Dalradian, mica ages are much younger than that 470 million years. The mica ages extend from 470 to as young as 410. So from Llanfian through to the earliest Devonian. And the mica ages record the cooling of the Grampian Highland block, the Dalradian block, through about 500 degrees centigrade for muscovite, and through about 300 degrees centigrade for biotite. So the fact that we have those ages from micas that cover the period from the early Ordovician through to the earliest Devonian must mean that the Dalradian, the Grampian Highlands, was uplifting throughout the whole of this time. The mica ages tell us that the Dalradian block, the Grampian Highlands, was uplifting. It was forming mountains through the whole time period of the later part of the Ordovician and the Silurian. If it's being uplifted during this time period, it must have been a major source of sediment throughout the later Ordovician and the Silurian, even into the early Devonian. How do we know this? Because we can see high-grade metamorphic zones that have been exposed within the Grampian Highland block. These would have been metamorphosed at pressure at depths corresponding to between 6 and 15 kilometers. So you have got to erode off the Grampian Highlands something like 6 to 15 kilometers of material in that period from the mid-Ordovician through to the early Devonian. Okay, you happy with that logic? Mountains give sediment. We know there were mountains because we know from the mica ages they were uplifting. They must have provided sediment. Where would that sediment go? It would go southwards, off the Dalradian block, into the Midland Valley, wouldn't it? Okay? So we would expect the Midland Valley to be stuffed full with sediment derived by erosion of these Grampian mountains to the north. What we actually have to the south of the Highland boundary fault is this rather strange bit of rock called the Highland Border Complex, which you had the pleasure of seeing in the field by the side of Loch Lomond. So let's talk about the Highland Border Complex. This is a suggested stratigraphic column through the Highland Border Complex, and it consists of 4 rock groups. A mafic to ultramafic igneous assemblage. You've seen the serpentinites in the field. There are also metamorphosed basic igneous rocks. You can see pillow lavas in some places. Sometimes they're metamorphosed so that they're hornblende schists. Dating of these metamorphosed igneous rocks ranges. In some cases, there are Cambrian ages. There's an amphibolite in Butte, which is just north of Arran, which has a 540 million year age. The basic igneous rocks have a wide range in chemistry, and they suggest that some are similar to volcanic rocks that we would see erupted today in ocean islands, and some would look like the chemistry of rocks that we see today erupted in island arcs. So this diagram here, which has concentrations of elements titanium, zirconium and yttrium on it, has been used to identify the tectonic setting in which old volcanic rocks were erupted or produced, and these fields stand for within plate basalts, WPB, within plate basalts. So that's where we would expect ocean island lavas to lie. So there's a red arrow going to the ocean island field in that diagram. And this area, LKT, stands for low potassium tholiites, or island arc tholiites, for those of you who were at yesterday's lecture. OFB stands for ocean floor basalts, so mid-ocean ridge type, but there's also an overlap with island arc tholiites. So some of the highland border igneous rocks resemble intraoceanic island arc rocks. The other rock groups, the igneous rocks, are overlain unconformably by a breccia. This contains clasts of serpentinite in a carbonate matrix, so calcareous matrix, and this is followed by limestone that contains trilobites and brachiopods that give a mid-Arenic age. So is that older or younger than the Grampian deformation, than the Grampian orogeny? Mid-Arenic. Younger? Older? It's older. The Grampian orogeny took the metamorphism deformation in the highlands, took place at the boundary between the Arenic and the Llanfearn, so late Arenic. So these limestones were formed just before the Grampian orogeny took place. There are then black shales, greywackies, and more pillow lavas, and these contain brachiopods that give a Llanfearn age. That's younger than the Grampian orogeny, if the Grampian orogeny is at the Llanfearn boundary. So we don't appear to have a break in the sequence here at the Grampian orogeny, and in the Llanfearn we have sediments that are black shales. It's not what you would expect to find in an area which has filthy great mountains developing just to the north, is it? There is then an unconformity, shown by that gap in the section, and then there are shelf sediments, deepish shelf, sandstones, limestones, some conglomerates, and they contain chitinozoa. Who likes paleontology here? I knew there was somebody, Chris. What's a chitinozoa? Anybody heard of chitinozoa?
Something that makes chitin in their shells.
I will show you some wonderful pictures of chitinozoa in a little while, okay? They're a microfossil. Anybody know any more about them than a microfossil? Possibly. I'm not sure what they're from. Anyway, chitinozoa, okay? And they're supposed to be of Coradic age, so upper Ordovician. So that's a picture of where we were. We were at Balmahar. We went and looked at the serpentinite about there, and the Highland boundary fault crosses Loch Lomond there, just to the north of a ridge of old red sandstone conglomerates. Highland border complex occupies that fantastically exposed ground just to the north. Remember how wonderful the amount of outcrop was around that serpentinite by Loch Lomond? Not really, was it? And you can see on this photo, that was rubbish photo, that there isn't actually much outcrop down there. Which has led to a degree of controversy in understanding what the Highland border complex actually is. There are two major groups of hypotheses, and they differ in how they interpret the Highland border complex in terms of how continuous the stratigraphic sequence is. Remember that there isn't much outcrop, so it's virtually impossible to get single continuous stratigraphic sequences that you can log through. You look at little isolated outcrops like the serpentinite we went to see. And also, there is considerable disagreement about the relationships between the Highland border complex and the Dalradian. So the first school of hypotheses developed from work by Brian Bluck from about 1983-84 onwards. Unfortunately, the papers that these were reported in are not available for download, so I haven't put them on Moodle, but they are available in the library in Transactions of the Royal Society of Edinburgh, and I would strongly recommend a little visit to rediscover where the library is and to read one or two of these papers, because they're quite good fun. Bluck writes very, very well. His view was that the Highland border complex is an entirely separate structural unit that was developed in a back-arc basin that existed to the south of the Laurentian continent and developed well away from where the mountains in the Dalradian were developing. He suggested that the Highland border complex and the Dalradian were brought together by strike-slip faulting or possibly subduction-related thrusting. And he suggests that the Highland border complex was amalgamated with the Dalradian, docked with the Dalradian in Devonian times, so well after the major metamorphism and deformation of the Dalradian. The second group of hypotheses has been developed by Tanner. There are a couple of Tanner papers on Moodle for you to look at. He proposes that groups 2 and 4 of the Highland border sequence, so that is this part of the sequence, okay, the upper part of the sequence, was deposited in a continuous sequence with the Dalradian. Group 1, however, which in this sequence are the mafic igneous rocks, ultramafic igneous rocks, shown here in the base of the sequence. Tanner regards these as being at the top of the sequence, and he suggests that they represent an ophiolite which originated as a volcanic arc, and that this was placed in the Arenig on top of the Dalradian and the remaining part of the Highland border sequence. Okay, so two very, very different views. We'll now have a look at some of the evidence that is in favour or otherwise of these views, and that links with some of the things we've seen on the geological maps in the practical. This map shows a cross-section from across the Highland boundary fault from the Dalradian into the major syncline, which lies in the lower Old Red Sandstone rocks to the south of the Highland boundary fault. And you'll have seen this on the Stonehaven map. There's an asymmetric syncline with the Old Red Sandstone being nearly vertical in the north and relatively shallow dipping in the south. And on that map, the Highland border complex is overlain unconformably by the Old Red Sandstone. So those of you who looked at the Stonehaven map, you should have seen that the Highland border complex, shown as basalt lavas, was to the south of the Highland boundary fault and was overlain unconformably by the Old Red Sandstone. There's also a little bit of Old Red Sandstone to the north of the Highland boundary fault, shown just here on this cross-section. And if you look really carefully at the Stirling map, you can see where there is Old Red Sandstone to the north of the Highland boundary fault. This has a gentle southeastward dipping unconformity surface. It's shallow dipping, unlike the steep dipping Old Red Sandstone to the south of the fault. And this little bit that's to the north of the fault contains lots and lots of Dalradian clasts. And the clasts in the Old Red Sandstone to the north of the fault show, or the sedimentary structures in the sandstones to the north of the fault show current directions towards the southeast. That's what you'd expect if you've got big mountains to the north. You'd expect current directions moving southeastwards. And that's what you have in the Old Red Sandstone to the north of the fault. To the south of the fault, current directions in the conglomerates are towards the northwest. And the clasts in the conglomerates, which you will have seen on the Stirling map and the Perth map, provided you found the one that wasn't a drift map, are largely made up of volcanic rocks. The clasts in the conglomerates are largely volcanic, and there is also quartzite, well-rounded quartzite clasts similar to the ones that we saw in the Old Red Sandstone conglomerates near Oban. So here, these are rich in lava and quartzite clasts. That's shown in this section here on the right. This shows the percentage of clasts in the conglomerates of different source as you go up the Old Red Sandstone sequence. At the base, quartzite clasts, then this bit is all volcanic clasts. This is a bit of quartzite clasts again. That's vein quartz. Very little in the way of Dalradian clasts. The clasts in the conglomerates to the south of the fault, which are derived from the south, remember I said paleo currents flow to the north, they must represent the southern edge of a basin because they're very coarse-grained. With paleo currents going northwards, sand-grade deposit would have been deposited further towards the north, where the Dalradian now is. You only get Dalradian clasts to the south of the Highland boundary fault in the uppermost part of the sequence, so quite late into the Devonian. Okay, are we happy with that logic? Bit of sedimentology for you? To the north of the fault, currents to take clasts to the south. They're Dalradian clasts. to the south of the fault. Current movement is to the north. The clasts are largely volcanic in origin. There must have been a substantial depositional basin in between the southern conglomerates and the northern conglomerates, which is now missing along the line of the Highland boundary fault. Evidence from the practical: in the Stirling and Perth maps, you should have seen that if you looked at the ornamentation for the conglomerates on the maps, something like 90% of the clasts are volcanic in the conglomerates to the south of the Highland boundary fault. So this led Bluck to the following interpretation. Also, going back to the Highland Border Complex, remember that the Highland Border Complex in the Caradoc and the Llanfair contains black shales, sandstones, no Dalradian clasts either. So the fact that we don't have Dalradian clasts in the Ordovician in the Highland Border Complex must suggest that the Dalradian block was not in close proximity at all. The Highland Border Complex has to represent a separate depositional basin from the Dalradian. Basalt chemistry suggests an oceanic basin, probably back arc in origin, and probably at least 200 kilometers wide in the Middle Ordovician, with a volcanic arc to the south. So here we have a sketch of that. Here is the back arc basin in the Llanfair. So this is just about the time when the Grampian orogeny is taking place. Back arc basin, oceanic basalts being erupted, oceanic sediments, black shales being deposited. Further to the south, a volcanic arc was proposed. So the Highland border might represent the original transition between the Laurentian continent to the north and ocean to the south. This hypothesis requires strike slip or subduction thrusting to juxtapose the Highland border complex and the Dalradian. And this must occur in the Middle Devonian because in the earliest part of the Devonian, as we've seen, we don't have clasts derived from the Dalradian. There's probably still got to be a 100-kilometre wide basin. So this is Bluck's reconstruction of the situation in the late Silurian to early Devonian. Here is volcanic arc still. Here are a basin in which old red sandstone sediments are being deposited on top of an Highland border complex underneath it, and then maybe eventually Dalradian somewhere off to the north. So this requires substantial activity on the Highland boundary fault until the middle of the Devonian. So that's Bluck's view. Highland border complex has a rather interesting structure. It's again struggling from the fact that there aren't that many outcrops. Did the Highland border complex experience the same tectonic history as the Dalradian? Think about the maps that you've looked at. Was there any map in which it looked like the Dalradian and the Highland border complex were deformed together? There were two maps where it looked like they were deformed together. Anybody think of them? On the Glasgow map, the boundary between the Highland Border Complex and the Dalradian looked like that. So that the Highland Border Complex was to the north of the Highland boundary fault. Do you remember seeing that on the Glasgow map? I certainly pointed it out to a few people. Anybody seen that on the Glasgow map? There you go, look at it there, up there. And to get those sorts of structures, these have to be synclines that are plunging towards the northeast. So, what you saw on the Glasgow map, or at least what I know one of you saw, even though you didn't admit to it, on the Glasgow map, suggests that the answer to this question is yes, that the Highland Border Complex did experience the same deformation history as the Dalradian, which doesn't fit with Gluck's interpretation of the situation, of course. Let's just look at that bit of the Glasgow map again. Do feel free to look at it on your way out after the end of the lecture. Those folds, in order to see those folds, you must do some fairly detailed mapping, and the fact is there is virtually no outcrop in the area where those folds are matched. And I strongly suspect that the people who put those folds on the map put them on because they were of the opinion that the Highland Border Complex did experience the same tectonic history as the Dalradian, and they wanted to show on their map that it did. I think if you went there to the locations where those folds are shown on the map, you'll probably find very little evidence of them. I must spend some time going to look at them at some point. But there's not much outcrop. These could be an example of people putting on their interpretations of the geology onto the map. And this is an interesting aspect about geological maps. Probably when you looked at those maps this afternoon, you treated what you saw on the maps as fact. But some people looked at both the older and the newer Aran sheets, and there's a difference between the older and the newer Aran sheets. Quite a lot of differences, in fact. One of them shows an unconformity between the Old Red Sandstone and the Dalradian, and the other shows a fault in exactly the same position. Maps are interpretations. When you make a geological map, or many of you make a geological map next summer, you have to distinguish between what is interpretation and what is actual factual observation. So you have to be very careful with that. There are different interpretations of the geology in the maps that we've looked at this afternoon. So I'm not convinced that what we see on those maps actually provides evidence to say yes to that question. We do have middle to upper Ordovician fossils at several localities within the Highland Border Complex. However, the Dalradian was deformed at 470 million years, which is early Middle Ordovician, and it can't deform middle to upper Ordovician rocks. That suggests that at least part of the Highland Border Complex is younger. The Gluck view is that the Highland Border Complex underwent penetrative deformation, cleavage formation, in the upper Ordovician, and then faulting through into the Devonian. There are lots of good papers on the Highland Border Complex. especially these three in the right here in the Geological Magazine. I tried downloading that, but it's not available. You'll have to go and look at it in the library, but I would recommend looking at those. More recently, Tanner and Sutherland reinvestigated our friendly Titanozoans from the Highland Border Complex. And specimens C through to F are the Titanozoa that have been described from the Chiratid-Titanozoa that have been described from the Highland Border Complex. If you want to know what a real Titanozoa looks like, it's A and B. Can you, hand on heart, distinguish or any sort of similarity between C through to F and A and B? Maybe if you're a Titanozoan specialist, but Tanner and Sutherland regarded these things as organic artifacts rather than Titanozoa. They suggested they were fragments of algal mat or bituminous infills of pore space. And Tanner and Sutherland proposed instead that the young Ordovician ages were not correct, that the fossils had been misidentified as Titanozoa, and that the bulk of the Highland Border Complex was deformed along with the Dalradian. The ophiolite of Arenig age lies on top of the sequence, and they think it was abducted on top of the Taynap. So these are two very different models. The Bluck model on the left, showing the Highland Border Complex with the ophiolite at the bottom, the Dalradian thrust on top late on. Tanner's model with the Highland Border Complex as part of the Dalradian sequence, Dalradian at the bottom, with the ophiolite placed at the top. Which is correct? Don't know, really. Read the papers, see which you think is right. Evidence from the practical. There is the Glasgow map showing the interfolding or apparent interfolding of the Highland Border Complex in grey and the Dalradian. This implies a fold plunging to the northeast. But outcrop is very, very thin in that area, so whether you believe that or not, that's up to you. And in Arran, we have no obvious Highland boundary fault. If Bluck was right, the Highland boundary fault is should be a major terrain boundary between blocks of crust with very different history that should be visible right the way across Britain. It's very difficult to identify where it is on Arran. Okay, so we'll now move on to the southern margin of the Midland Valley. The oldest rocks in the southern margin are in the southwestern part, near the town of Girvan, called the Ballantrae Complex. This contains serpentinites, gabbros, pillow lavas, cherts, black shales, oceanic lithologies suggesting an ophiolite. There are two serpentinite bodies, one there and one there, and both of these serpentinite bodies have metamorphic soles that are up to 100 meters thick. So there's metamorphism directly below the serpentinite body, where the grade decreases downwards from high grade next to the ophiolite to green schist lower down, suggesting that a hot mass was in place tectonically about 480 million years ago. There's some pillow lavas in Ballantrae. The lavas have been dated between 500 and 480 million years using Sumerian neodymium, and they have a complex chemistry that includes both ocean ridge, ocean island, and also island arc lithologies. So these sorts of diagrams we were talking about in igneous yesterday, and I suggested that there were, in modern volcanic rocks, there are substantial differences between within plate and ocean ridge lavas and arc lavas. Arc lavas show very spiky patterns for elements such as strontium, potassium, barium and so forth, and show these big dips at niobium. So how do we tell that they have all these lithologies? Modern basalts of this distinctive trace element chemistry. Arc lavas in particular are very poor in niobium and very rich in lead. That's lead on the left-hand end there. These are chemical plots for rocks of the Ballantrae complex showing lanthanum-niobium ratio, and we have a variety of parts of the Ballantrae complex which are arc-like in chemistry, and other parts which are like Morb, and other parts which are like ocean island lavas with very low lanthanum-niobium ratios. This wide variety in chemistry suggests formation in a back arc environment and tectonic amalgamation of the igneous rocks from a variety of sources. Sediments overlying the igneous rocks include graptolitic shales, which are Arenig in age, early Ordovician, and then conglomerates that mostly contain igneous debris. So interestingly, very similar ages, very similar lithologies to the Highland border complex. Unconformably above the Ballantrae complex are conglomerates of Caradic age, Upper Ordovician. So this is Caradic, Llandilo, Llanvian there. So we've got these conglomerate bodies that get thicker towards the northwest. And the lower conglomerate is mostly made up of clasts from Ballantrae, probably formed in a deltaic or fluvial environment after the abduction of the ophiolite, and we got shallow marine limestones. The upper conglomerate, this one, includes a large number of undeformed granitic clasts, such as this one. Sadly, we only have one specimen left. You can start passing it around, or pass it back to me so I can then pass it around. Okay? Okay, if you pass it to Emma and then pass it onto the bench behind you. These granitic clasts in this conglomerate go up to 3 meters across, and they give ages between about 560 and 460 million years. So they're very similar in age, these clasts, these granite clasts, to the sediments that contain them. They're associated with volcanic clasts, basalts, andesites, and rhyolites, which suggest erosion of a volcanic arc complex. And that volcanic arc complex must be nearly the same age as the sediments. Because the granites are 3-meter sized boulders, they have to be very local in origin. You couldn't derive 3-meter boulders from the highlands, for example. These 3-meter boulders must be derived from within the Midland Valley, and this provides key evidence that we had a volcanic arc in the Midland Valley in the Middle Ordovician. Going upwards into the Silurian, there's a change to outer shelf facies in the Caradic, and then some turbidites. Faunas in the Ordovician in the southern Midland Valley, very good paleontology, very similar to those in North America, though this starts to develop a similarity with Wales in the uppermost Ordovician. There's a slight unconformity between the earliest Silurian, the Llandavri, and the Ashgill. Llandavri shelf to slightly deeper water, which you can see by the brachiopods in them. Brachiopods in the Silurian are characterized by different depth communities. Later in the Llandavri, within the lower Silurian, there's regression, and we start to develop a continental red bed facies as early as the upper Llandavri in the southern Midland Valley. So that even in the Wenlock, we're getting desiccation cracks. There's clearly subaerial exposure, starting to get continental sedimentation. In the late Wenlock, we get conglomerates containing volcanic clasts that are probably alluvial and mark the start of the old red sandstone facies, the continental facies. So continental facies in the southern Midland Valley started in the middle of the Silurian. Sorry? Middle, late Wenlock, that is, okay? Wenlock is middle Silurian. Going up further in the Silurian, we have fluvial sandstones with very well preserved fish. And these are conformably overlain by what is conventionally called the lower Old Red Sandstone in the Hamilton map. Those of you who drew that cross-section will have seen that the folding on the Hamilton map post-dated the lower Old Red Sandstone. There was a conformable sequence all the way from the Silurian into the lower Old Red Sandstone, the early Devonian. Other areas in the Midland Valley, in the southern Midland Valley, the early Devonian is unconformable on Silurian rocks. So, for example, on the Edinburgh sheet, you will have seen an unconformity. And the fact that there isn't a regional unconformity must mean that there was only localized deformation between the Silurian and the Devonian. In other places, there's continuous sedimentation. Within the southern Midland Valley, there is no obvious indication of derivation of clasts from either the southern uplands or from the highlands, all the way through or almost all the way through the Silurian. Only towards the top of the Silurian there is a conglomerate called the Greywacke conglomerate. It's shown on the Hamilton map. That may be derived from the southern uplands, which, as you know, are 99.5% Greywacke. Most of the metamorphic clasts in the conglomerates in this sequence are our friendly large quartzite clasts, polycyclic quartzites, and we don't really know where they come from. They're present in all of these old red sandstone rocks. So, based on the Hamilton map and the Edinburgh map, the Silurian was deformed before the deposition of the upper Old Red Sandstone. It was deformed in the middle Devonian, and the southern upland fault moved after the deposition of the Old Red Sandstone. Final issue, what is there beneath the lower Paleozoic rocks in the Midland Valley? Could there be oceanic crust? We've said that there are oceanic rocks at Ballantrae and ophiolites. We've said there are oceanic rocks in the Highland Border complex. So could there be oceanic crust beneath the Paleozoic sediments of the Midland Valley? This would have a very strong magnetic and gravity signature, which are absent. Seismic refraction studies tell us that the Midland Valley crust is normal continental crust, about 30 kilometers thick. Could it be Dalradian metamorphics? This seems unlikely because there seems to be very little in the way of Dalradian clasts within the lower Old Red Sandstone and lower Paleozoic of the Midland Valley. Seismic refractions suggest that we have a basement that is like the Lewisian, a granulite facies basement. The later Carboniferous volcanics contain xenoliths derived from the deep crust in the Midland Valley. These are mafic granulites, which represent metamorphosed gabbros, and these probably are fragments of deep layered igneous complexes in the lower crust, a bit like Skaergård in the lower crust of the Midland Valley. There are also felsic granulites, which tend to be highly deformed. Some of them were metasediments in that they contain some selemonite and graphite, but mostly they're the xenoliths are of igneous origin. The mineral ages in these xenoliths suggest cooling at about 400 million years to 600 degrees centigrade. There. And this suggests that the lower crust may in fact largely be the Ordovician and Silurian volcanic arc that we can see evidence of being passed around in that granite boulder. Sorry, it's not a 3-meter one. So to summarize, this shows a Midland Valley that is pulled apart from its current width. The clasts that we see in the Benin conglomerate, that's one that's going round, suggests that there has to be a volcanic arc complex shortly to the north of Ballantrae, maybe 5 to 10 kilometers north of Ballantrae. So here we have a volcanic arc complex in the middle of the Midland Valley. This volcanic arc complex appears to have persisted in the Midland Valley right through till the lower Devonian, when we get arc-like volcanic rocks persisting. The xenoliths that we see in the Carboniferous lavas could be from plutonic rocks that formed part of the plutonic complexes underlying the volcanic arc. To the north of the arc, there was a back arc basin in which the highland border complex may have been deposited, depending on whose models you believe, but probably the highland border ophiolite at any rate represents a back arc basin to the north. And to the south, there were a series of 4 arc basins, so between the arc and the trench. These would be the basins that we find in the southern Midland Valley in the lower Paleozoic. And that concludes my talk. Any questions? I will put up answers to the maps on Moodle. You should have seen answers to the Ben Nevis map that I've got on Moodle as well. Yeah, good. Have a nice weekend. And I will see you next week for the Southern Uplands. 99.5% There is a sign-in sheet. I don't know where it's got to. Where did the sign-in sheet go?